Okay, the global atmospheric circulation model is about the surplus energy at the equator and the excess or deficit energy at the poles, and how this allows the transfer of global heat energy. To create this balance, there's a constant sort of energy transfer from here to here, or on the southern hemisphere as well. It's not as straightforward as this though, because what happens is air moves from high to low pressure all the time. So the equator is an area of low pressure and the polar areas are areas of high pressure. This is why the air moves in these cells. If we think about this idea, it's because there's always a balance needed. In areas of low pressure, where there's clouds, you have water vapour evaporating up and condensing when it cools to form clouds. So any mass of air at an area of low pressure, such as this one here, the air is moving upward with the water vapour. And at the same time, when you have air here, what happens is this denser air, which has an absence of water vapour, wants to fill in the space to create an equilibrium. Because of this, what you end up with is this happening. If we look at this model, I've taken the Earth here and I've flipped it the other way around. So we have the equator in the middle and then the tropics, well, near enough the tropics at the 30 degrees south and 30 degrees north. What happens is, because the sun's insolation is its strongest at this point, we have any air that's here being heated and it rises up next to it, forming low pressure bands. As it starts to rise up, because it's higher up in the altitude from the ground's obviously the hottest part, as it rises up and it cools down, it forms clouds and condenses. So this will end up travelling towards areas of high pressure. The high pressure at the North Pole and the South Pole, there's high pressure too, so it moves this direction. Then what happens is it rains. This air naturally will sink down like this at each side, and because we now have high pressure here, this will move towards the equator where there is low pressure, like this. This completes the first cell. This completes what is called the Hadley cell. And this Hadley cell is one of the key drivers in helping this belt, or this sort of conveyor belt approach, happen. Now this will go on with every single cell, as we can see here. But what also goes on, if you look carefully, is it ties into the ferro cell. So the cold air goes up, it sinks and gets pulled back. But some of this air, as opposed to coming back this way, will diverge, it will split to either here or here. Di means two, like uni means one. It moves this way. Some air of course converges together like this, creating a sort of thermal vacuum, like the International Tropical Convergence Zone that you've also seen. Now what we need to do is look at what happens next. So if you have a pause of the video, you can read the model answer that's here. But what we went through so far is this idea that these different cells, if you name them, it will help with your mark. But a polar, Hadley and ferro cell circulate the air in the atmosphere. So warm air is less dense and rises at the equator before cooling and spreading 30 degrees north and 30 degrees south where it sinks. Some of this warm air travels towards the poles as surface winds. This occurs, okay, so we need to talk about that. Okay, we've missed this bit, we've done this bit. The remainder returns to the equator to be reheated. This completes the Hadley cell, which is thermally direct, as in it's directed through heat. A zone of divergence occurs at this point when it diverges, okay, to the north or the south pole, depending on what part you're looking at. So let's go over this bit here again. So what happens is, after it sinks, some of this will be pulled into this area of low pressure, from high to low, remember, and it's drove towards this ferrule cell, okay, just around the UK. It's around something like 60 degrees north. Okay, at 60 degrees, the warmer air travelling towards equator meets the cold air travelling across the surface of the earth. At this point, the two converge and rise up into the atmosphere. As we can see, this happens right here, converging and sinking, completing the ferrule cell. The surplus energy, which is left over, is carried in the warmer air towards the poles. It then sinks upon cooling, creating the polar cell. This cell is also thermally direct. So if you look here, you can see how this is pulled a little bit further up here, and then it can get caught into this polar cell of high pressure. Now remember, this is furthest away from the sun, so you're not going to have much heating. So any air that's here is just going to sink because it's very cold, but it's very dense. Another thing that you can notice in this diagram is how the Coriolis force dictates how the air travels, as well as the differences in direction, whether it's the northern or southern hemisphere. Okay, so if you pause it here and look through that, that should be fine for the full marks in this answer.